G'day everyone. We are really happy to be able to present to you our presentation that we presented at BSidesSF back in 2019.
Woo! Awesome. Can everyone hear me with my funny rock and roll microphone?
Test.
Okay, cool.
We thought we would take this opportunity to re-record bits and pieces of it and make it a little bit more slick. At a high level, what we want to talk about is trying to shift this mindset of JavaScript being a language that people maybe don't think very highly of, and instead trying to bring it into the realm of offensive security testers and red teamers and bug bounty hunters.
Let's do some intros. My name's Dylan. I've worked at a number of large tech companies, I've open sourced a number of popular tools, and I've spoken at a number of large popular conferences, including DEF CON 2018 and DEF CON Black Hat of 2020.
My name is Christian Frichot. I recently moved back to Australia after spending a few years working up in the Bay Area for a couple of software companies and startups, and now currently work for HashiCorp remotely doing product security style work. Before that, I was fortunate in that I got to contribute to some projects such as the browser exploitation framework and also the browser hackers handbook published by Wiley.
Okay, so first a little bit of context. In 2018, Christian and I originally gave this talk on stage at KiwiCon in front of a live audience, and we did something that I would consider fairly gross. And I told Christian we really did not need to do it again for this talk, but despite my best efforts, we have to get on to some actual content. This talk is about moving from JavaScript running in a web browser to a malware implant running on a server behind your private network as quickly as possible. We're going to talk about how we can do that using some JavaScript APIs that include fetch, WebRTC, service workers, and a couple of others. And we're going to augment it with some red teaming reconnaissance techniques to make it as efficient and quick as possible.
And of course, we can't forget all the other JavaScript features such as MathML, SVG, Canvas, Index Database API, File API, Media Capture API, WebSockets, Web Workers, Geolocation API, Offline API, Web Notifications, WebGL, WebAssembly, Web USB, web pretty much everything.
Fucking web browsers.
And one of the topics that we'll talk about a little bit later on is that actions can be performed cross-origin, despite the controls in place in browsers with regards to the same origin policy.
Let's rewind the clock to the early 2000s. There used to be a time when an attacker used to be able to just directly and very easily find a vulnerability like a SQL injection or remote code execution that could just directly give them access to the production database and give them access to all of the user data, passwords, and payment information for all the different users in the system. Over time, defensive application security has gotten better in these regards, and it's a lot more difficult to find these types of vulnerabilities that just directly take you to the most juiciest data. But offensive techniques have also evolved. Today, sophisticated malware frameworks can be used to pivot laterally through an environment where you may start an attack chain with a malware implant on a developer's laptop, kicked off by a spear phishing campaign. That infected laptop can be used to compromise other internal servers. And because many services on the inside of company networks are less secured than the servers on the outside of a company's network, the attacker can use their arsenal of malware exploits to move from the original compromised laptop to an internal server, to another internal server, to another internal server, until eventually they get access to the same juicy data that they used to be able to get access to through a single vulnerability. Through these post-exploitation malware frameworks, it's still very easy for an attacker to get access to the data they're looking for, and this remains an unsolved problem in the industry today.
Most organizations suffer from this problem that we've coined the lobster security fallacy. It's often called the Cadbury cream egg fallacy, and the idea is that an organization's security controls are often hard on the outside and then really, really soft and delicious on the inside. And all of this really comes back to that initial foothold, like how you can get access into a network and how things like the prevalence of web browsers and their connectivity to multiple networks and, 1,000 tab fatigue syndrome. These are all interesting avenues that, someone with some malintent could take advantage of. The first item, obviously, on the attacker's to-do list in these scenarios, such as making a user click a link, there's many different ways that this can occur. Over the last few years, we've seen prevalence of things like phishing and social engineering, random website compromises, watering hole style attacks, even, all the way through to more complicated web app vulnerability related problems such as monster in the middle style attacks or cross-site scripting and things like that.
Here's some interesting information from one of the Verizon data breach reports. If that initial malicious email contains a malware attachment, there's about a 12% chance of the user downloading that attachment and detonating it. But if that initial phishing email just contains a link that takes the victim to malicious JavaScript, there's about a 30% chance that that victim will click that link.
And so we really have to ask ourselves, just how bad can clicking a link be? We think that it is bad. It can potentially be quite bad.
Yeah, and there's also some misconceptions around opening up links in incognito windows and things like that. And it should be worth noting that all of the attacks that we're going to be going over today can be performed in an incognito window just the same.
If we look at what a client-side JavaScript-based attack flow might look like, you can start to lay out this pathway of these escalating steps that can occur inside of the document object model. User clicks a link, bad website, gets the user's internal IP address. Bad website then uses that information to try and sweep across that network, in spite of the same origin policy. Then JavaScript try to exploit some stuff based on the limited information that it may have. And I think looking at browsers in this way as an attack surface is really, really interesting, because if you think about it, your web browser is connected to probably at least 3 different networks at any one time. It'll be connecting to the local network, potentially through something like Wi-Fi. It might be able to connect to the internet through Wi-Fi or through like 4 or 5G. And also it will be able to access things like the loopback on the computer or even on the phone itself. And let's not forget about the potential for your mobile phone to also roam from local network to local network to local network, as you might move around between your personal Wi-Fi at home or your corporate Wi-Fi at work.
So a few times we've mentioned the same origin policy, and we've mentioned it's not going to be an issue for us for jumping from a malicious website on the internet to an internal server. To understand why this is the case, let's jump in a little bit to an example and see if we can wrap our heads around the same origin policy. To start out, I'm running a local web server on the loopback interface, and I've browsed to a malicious website, evil.com. I've also pulled up console here so that we can run JavaScript commands from the context of evil.com. We'll start with a simple example. I'll just send a post request to evil.com from evil.com using the fetch API. It goes out without any issues. Next, I'll make it a little bit more interesting by reading the response. And again, we can see we're able to read and log the response here without any issues. Now, to make things a little bit more interesting, let's send a post request to the web server that I have running locally. What's interesting here is we do see an error after we send the post request. There's a message here that talks about cores, but if we check the server logs, we'll see that a post request actually was sent to the server. Because HTTP requests are meant to be these really stateless request response one and done transactions, from the web server's perspective, they don't know which origin the request originated from. They just see the post request, and that's kind of the end of the story. But now the browser is throwing this funny error. But if the request already went through, what's the error all about? Well, to understand that, let's try to read the response from the web server. Now, all of a sudden, when we try to read the response from the post request, we're unable to. We can't log the response. We get the same error that we got before. Let's try one more example. Now I'll change the method from post request to a put request, and we'll try the same thing. Now something really interesting happens. In the server's logs, we no longer see that a put request went through. Instead, we see an options request went through. That's not what we asked for. We asked for a put request. So what's going on here? Why is it that we're allowed to send some requests across origin, but not allowed to send other requests? And what's the deal with being able to read responses?
In the context of web browsers, the same origin policy is one of the better controls that we have to constrain the execution environment of JavaScript in one tab from being able to kind of interact with data from a different site or origin. You might have two tabs open, and obviously JavaScript in a Google tab should not be able to interact with an API or a service, or even JavaScript itself, which is on like a Facebook origin. At a very high level, they're split into what we call simple HTTP requests and non-simple HTTP requests. A simple HTTP request might be something as simple as when you click submit on a form and that data gets posted to like a URL. And pretty much non-simple HTTP requests are kind of almost everything else. You know, a good example would be is if that you wanted to submit using JavaScript a request to an origin that maybe included some custom HTTP request headers. What actually happened is that before the web browser actually submits the legitimate request, it sends a HTTP options request to that target origin to try and get, basically say, hey, do I have the permission to perform this request? And what that's actually doing is it's shifting the control to the target origin to basically allow them to kind of specify whether they're able to retrieve your requests or not.
Understanding all of that helps us understand what the same origin policy is, and you can already start to see that there are some ways which we can jump from a malicious website to a local web server in spite of the same origin policy's restrictions. The differentiators between a simple HTTP request and a non-simple HTTP request can sometimes seem a little arbitrary. Check out this resource from Mozilla to see the full breakdown, but at a high level, a GET request or a POST request with no extra headers or anything modifying it outside of what a regular form post would be able to do is a simple HTTP request, even if it's initiated from JavaScript.
Some cross-origin requests can be used to exploit vulnerabilities. So for instance, cross-site request forgery is a good example. In these instances, you can actually submit the request and you might not even care what the response comes back. If that request is actioned on by the server, that might be good enough for you as the attacker to be able to proceed with your chain of attack, which is where anti-CSRF tokens have become a very common control to protect against that. The other thing that obviously SFP doesn't really help too much out with is DNS rebinding, which we'll cover a little bit more later. Now, at a high level, the idea behind the same origin policy was that it should be able to prevent and control data that can be sent from origin to origin. But the nuance of how it actually works and how browsers work, there are always use cases where even sending HTTP simple requests, such as requesting an image, that will obviously always go without this pre-flight request. And what's interesting in those circumstances is you're still effectively sending a cross-origin request. And even though you might not be able to get data back, it still does leak timing information.
Most importantly, for our purposes, these CSRF attacks and timing leaks can be used to jump from one network to another network, as was shown in our example where we started on a website that was on the open internet and were able to send a post request to a web server running on a private network, in this case the loopback interface. But really it could be sent to any network that the device, whether it's a phone or a laptop, is currently connected to.
So one of the concepts that we really liked and was kind of trying to think about cross-site request forgery in a different lens. And instead of trying to use it to target an individual and make them perform some action against their own personal account in some web application, we thought it's more interesting to think about this in the context of attacking infrastructure. Not just using CSRF attacks to attack users, but against like bigger things that may be users within a corporate network. And that's kind of one of the ideas behind Beef. It was really about this beachhead of having a browser inside of a secure context and telling them to perform actions. When we start to look at exploiting cross-site request forgery attacks in the context of a greater environment than just a user's web browser and their current authentication status to like a web app, this starts to look really interesting because now we've got this ability to be able to send requests that are potentially bypassing net controls that may be in place, such as firewalls. You might be in an environment where there's a whole bunch of colleagues who happen to be sitting on the same network and potentially they're running local insecure stuff on their developer workstations. As we kind of touched on before with the lobster fallacy, it's very typical that your laptop or your computer, when it's in your corporate network, has access to servers and resources that definitely were not designed or secured against the internet. It kind of comes back to that hard perimeter but soft from the inside. But once you kind of get some control of any origin inside of a corporate network, you can potentially start interacting with these other servers on internal networks. So for those that haven't ever spent time using the browser exploitation framework, this is a look at what the UI is when you start and log into Beef. In this example, I'm hooking an Android mobile phone into the framework. And once they're hooked in, you'll see them appear on the left-hand side under the online browsers. If you click on a browser, the first thing you'll basically receive is all this information associated with that hooked browser context. So the date stamp, the reported name of the browser, which may include like the phone type. You can click through to the next page and you can potentially see some other information that's kind of somewhat passively been acquired from that hooked browser origin. From the commands tree, there's a bunch of different commands that you can execute, but the one that we're interested in is this get internal IP with WebRTC. So a little bit of background on web real-time communications. The intent behind this technology was to provide a mechanism for browsers in a cross-browser style method to be able to connect to each other and stream media or other data channels between each other. WebRTC had to implement some mechanisms to allow browsers to connect to each other. And a part of that was effectively this protocol called ICE, or the Interactive Connectivity Establishment Protocol. Now, for this to work, what actually had to happen was the browser had to query a local API to effectively figure out what all the local IP addresses were. You might have a number of computers that are actually on a pretty local network, and for them to talk to each other directly, you don't even need to have that communication go out through the internet. For that obviously to work, you had to be able to determine your local IP addresses. Between the time of when Dylan and I first put this presentation together for KiwiCon and now, there have actually been some privacy enhancing changes being made to some of the mechanisms used by WebRTC inside of modern browsers. The method that they've used to prevent the leakage of internal IP addresses has been fully implemented inside of desktop browsers, but actually hasn't been implemented yet in mobile phones. I wouldn't be surprised if this change will come through pretty soon. Now, there's obviously other ways that same information can be gathered. It was just interesting to see how, the needle as far as browser security controls have been implemented is a thing that obviously does change over time. What actually happens now is that when Chrome, for instance, requests a local IP address, it actually interacts now with multicast DNS service provider inside of the browser and effectively generates like a randomly generated multicast address that the browser will answer. So if anyone's in the local network and then try to discover where that computer is, the browser will actually respond now to multicast DNS, which is quite interesting.
Future research topic.
In this instance, you can see that the execution of this has basically provided us with a 192.168 internal IP address. And this is quite interesting because using that information, we can actually use another module called ping sweep, and we can feed it effectively like a range of IP addresses somewhat associated with the starting point of that initial hooked browser inside that phone. And we can kick off a task that basically will get executed in that hooked browser. The ping sweep module is interesting in that it just tries to submit like a cross-origin style request to the target IP address. And it then makes a kind of guess on how long that initial kind of request will either take to error out or potentially return some content. And using that information, it can basically give you a determination on whether or not a host is available at that IP address or not. So this is a really good example of JavaScript that's executing. It's sending requests out across an origin. And due to the way that the SOP works, we can actually make assumptions around information based on the timing of data that may or may not come back. Now, Beef obviously has its challenges and limitations as well. A really good example is what if the victim closes their tab? At that point, you potentially lose the JavaScript execution environment that maybe you were using to perform reconnaissance or perform exploitation of internal resources, and that's obviously not ideal. And I guess like one of the things that we really wanted to try and figure out was like, how bad can it be if you can gain access to arbitrary JavaScript on a single victim, within like a corporate network, and maybe potentially you've only got about 60 seconds to execute as much as you possibly can.
There's one other type of vulnerability that we need to touch on really briefly in the context of attacking infrastructure, and that's cross-site scripting. Most people have heard of cross-site scripting, and the reason is it's, according to HackerOne, the most popular web vulnerability. It's so popular that AppSec teams have actually, in my experience, grown a little bit numb to it. At a high level, cross-site scripting is basically gaining untrusted JavaScript execution on a trusted website. So when an attacker can run JavaScript on an origin that they shouldn't be able to run it on, that's cross-site scripting. Now, in its typical form, it's used to attack other clients. But again, let's frame this in the context of being able to attack a server. First, let's look at a quote from HackerOne. In this quote, they heavily imply stored cross-site scripting is generally more severe than reflected cross-site scripting. The difference between stored cross-site scripting and reflected cross-site scripting is stored cross-site scripting is when you manage to get one of these unsafe JavaScript payloads saved into a database. It can later be read back out and executed in their safe browsing environment. Reflected cross-site scripting is when the cross-site scripting payload is in the URL. So you can see why some AppSec engineers may just assume that the stored cross-site scripting is more severe because it persists. But let's think about this from the perspective of a private network. Let's say I, an attacker, want to trigger cross-site scripting on a victim based on the fact that they have access to an internal service. I'll pick an example internal service, let's say Jenkins, and let's say the attacker has advanced knowledge both that this victim is sitting on a network that has access to this Jenkins server, and the attacker has obtained a reflective cross-site scripting for Jenkins. In this scenario, all the attacker needs to do is send a link to the victim, and if clicked, it'll detonate the cross-site scripting from behind the private network in the Jenkins environment. And because we're talking about Jenkins, that means that that JavaScript will be able to interact with Jenkins in a way that will get arbitrary code execution on the server. Jenkins, by design, allows users to run arbitrary code. So, being able to impersonate a user's JavaScript enables the attacker to be able to run arbitrary code on the server. But what would this look like in the case of stored cross-site scripting? Well, in that example, the attacker would need some way to get that cross-site scripting payload saved into the database. And remember, they don't actually have direct access to this web app. It's behind a private network. So in this particular example of attacking infrastructure, reflected cross-site scripting is actually much more valuable to an attacker than a stored cross-site scripting. It's also kind of interesting that if we look up the vulnerability ratings for cross-site scriptings historically against Jenkins, they've all been pretty low severity, as opposed to a remote code execution vulnerability, which might have a max 10 out of 10 severity. This is interesting because a cross-site scripting not only equates to remote code execution, but through the browser's usage of multiple networks can be leveraged in a way that enables an attacker to gain that code execution even though they don't have direct access to the network. In that capacity, a reflective cross-site scripting in Jenkins can actually be more dangerous than certain types of remote code executions. At this point, you're probably wondering, okay, you might be able to construct these URLs with cross-site scripting in them and attack a company if you knew what the internal host names were and you knew where people were running their Jenkins and things like that. But if you're trying to attack a company, you wouldn't know any of that stuff ahead of time. So how is any of this helpful? This is where some red teaming reconnaissance starts to enter the picture. We'll go over a few different tools that are going to be useful in figuring out what these internal host names are. But before we get into that, we need to pick a target company. Now, there's basically no way for us to do this without somebody getting a little bit mad at us. So I'm sorry, Pinterest. Now, it's worth noting that neither Christian nor myself have ever worked at this target company, and for no reason other than just needing an example, we decided to pick on Pinterest. There is nothing extra vulnerable about them. If anything, this is categorically an example Silicon Valley company that roughly matches what you would find running these same recon techniques on any other major company you can think of. To start things out, I'm going to show off a tool called RiskIQ. RiskIQ uses a technique called passive DNS to collect a bunch of data and information on lots of different websites. The way passive DNS works is they have some sort of tap and internet infrastructure, and they watch DNS queries fly over the wire. Because DNS queries are not encrypted, they're able to see this data and collect it and then use it for their product. So we'll start just by searching Pinterest. At this point, we can see that there are a bunch of SSL certificates that RiskIQ has observed. And what's interesting here is you can expand them and see all of their different fields. And RiskIQ allows you to actually do reverse searches on all of the fields on the SSL certificate. So when we see the organization name for this certificate is Pinterest, we can actually do a reverse search on that, and we can see every other SSL certificate that uses the name Pinterest for the organization name. This takes us to a domain called pinadmin. Pinadmin, as it turns out, is one of the domains that Pinterest uses internally to host some of their internal tools. You might be thinking that they can just remove some information from their SSL certificates to make this a little bit harder to find. But the reality is, this information actually leaks out a number of different places. One tried and true way that I like to find internal host names is through the company's mobile applications. Typically speaking, information leaks out in the mobile application because it's designed to function both on the internet and in an internal test environment. And so we can often find references to that test environment buried in the app. To uncover that, we can use an APK decompiler to get access to some of the raw Java class files that contain information leaks that we'd be looking for. After we've downloaded the decompiled Java code, we can just run some simple string greps, and sure enough, here again we can find a reference to pinadmin. One other simple way we can get access to this host name is if we just head over to Pinterest's GitHub and search their organization, we can again find dozens of references to pinadmin scattered throughout their open source code. Lastly, there's a tool called CertGraph, and I've invited Ian Foster, the author of CertGraph, to show off how the tool works and how it can help us find more domains.
CertGraph is an open-source intelligence tool to enumerate related domain names by crawling the graph of publicly trusted certificate alt names. There are many sources it can pull data from, but by far the richest is certificate transparency. Certificate transparency is a publicly auditable log of all trusted SSL certificates, including internal SSL certificates and internal domain names. CertGraph works by finding all the SSL certificates for a provided domain name, finding all of the alt name domains listed in all those certificates, getting all of their certificates, and iterating appropriately. This can allow CertGraph to enumerate lots of related domain names and subdomain names shared by the same entity that would otherwise be hidden. For example, this can help enumerate domains like pinadmin.com from Pinterest.com if they share an SSL certificate, or even if any chain of domain names and certificates is shared between them. Using Dylan's example, if you run CertGraph on pinadmin.com, this reveals many other subdomain names of pinadmin.com as well as pin220.com, which looks like another interesting domain that might be worth looking at.
There are a number of other tools that can be used to find internal domain names, but let's shift our focus and look for subdomains at this point. One popular tool I like using for this is Sublister. Sublister in itself will actually use a whole bunch of other tools to find subdomains, which include searching VirusTotal for samples that people may have uploaded, Google dorking, certificate transparency, and a number of other things. And using this, we can find more than 200 internal subdomains of pinadmin. With this information, there's one other type of attack that we briefly mentioned earlier, and that's DNS rebinding. DNS rebinding in the context of a browser is another way to kind of skirt the same origin policy. If we look at the simplest definition of an origin, it's the protocol, the domain, and the port. Notably, the server's IP address is not a consideration when defining an origin. This means that when the browser is doing DNS resolutions to obtain an IP address, if it performs a second DNS resolution on the same host and the IP address changes, the browser will consider it the same origin, even though it's a different IP address. Let's think about this from the perspective of a malicious website. You may browse to a malicious website which resolves to a public IP address that belongs to an attacker. Then, the attacker might try to use the fetch API to have your browser make a request to their domain. However, if the second resolution doesn't point to a public IP address anymore, but instead points to an internal IP address, the attacker has orchestrated a way to force a victim to send a request into an internal IP address while the browser still thinks it's talking to the same origin. Because it thinks it's talking to the same origin, all the rules that we mentioned about simple and non-simple HTTP requests go out the window, and the attacker is freely able to make requests and view responses from whatever web server happens to be on the other side of that IP address. Likewise, we can do something similar with a CNAME rebind. Instead of binding to an IP address, we can rebind to a CNAME. And by doing this, we can just CNAME to one of the hosts that we found in the previous enumeration. This then enables an attacker to load a malicious web page and then have a victim go to that malicious web page. And the JavaScript on that page is now free to send requests to internal hosts that the attacker doesn't otherwise have access to, view the response, and proxy it back out to the attacker. The attacker can then use the victim's web browser to effectively form a proxy between them and the internal network that they sit on, and view all the content that sits behind the private network that they can DNS rebind to. There are a few limitations to this attack. First and foremost is the hosts that the attacker is targeting can't be running SSL. The reason is the domain will not match the domain that's listed on the certificate. That's because the domain is still the attacker's domain. Therefore, if you try to DNS rebind to an SSL website, the browser will just get certificate errors, and the attack won't work. Another limitation is some web servers, such as Django, will actually do a host header verification specifically to prevent this type of attack. If the Django web server sees the malicious host header instead of the host header that the server is expecting, it'll just drop the request. Additionally, if there are any cookies that are stored on the user, those cookies will not be sent through because cookies are saved to domains, not to IP addresses. So to frame this whole attack, you need an insecure web server internally that doesn't have authentication on it. And that's actually pretty common. I would almost wager to say common enough that if we were to rebind to all of the host names that we were to find in the enumeration step, we would almost certainly be able to exfiltrate some data that we shouldn't be able to. Here's another limitation. The DNS cache on a browser is actually 60 seconds, so you need to keep a victim on the page for 60 seconds to be able to perform this attack. That does not mean if you're targeting 200 domains, you need to wait 60 seconds for each domain. Instead, we can get around this by iframing 200 different iframes in the background and having each one of them point to a different malicious domain, and then at the end of the 60 seconds, we'll rebind them all at the same time and steal all the content from each of the iframes. Let's look at a brief example of this. So to frame the context, I've got two web servers running. One of them is running on the open internet, and one of them is running on loopback. Then I've got a secret file called secret.txt on the loopback web server that if visited /secret.txt, you'll see that there's some secret text here that we don't want strangers on the internet to get. Okay, with that context, let's visit the website on the internet and take a look at the JavaScript to see what it's doing. So we can see there's some very simple JavaScript here that's just trying to pull the origin for the page every second. And remember, the IP address is not a part of the definition of an origin. So when we check the server logs, we can see that the remote server is getting pulled once a second. Then I'll fast forward a little bit for 60 seconds for when the DNS cache in the browser expires. When the browser does a second DNS lookup, instead of returning the public IP address again, instead it's going to return 127.0.0.1 or the loopback interface. And all of a sudden we can see this very simple JavaScript that's just polling window.origin jumps from the remote web server to our local web server. And if we look at the IP address in the logs, we can see the remote web server was seeing an IP address come from the open internet, but the local web server sees that the request is coming from within the loopback interface. And all of this allows the JavaScript, which was loaded from the remote untrusted server, to actually read the /secrets file on the local web server. Now in this example, I've just written it to the DOM, but you could imagine it being exfiltrated out to the malicious attacker at this point. And you can imagine how we can use this to basically skirt the same origin policy.
Another browser technology that we have up our sleeves when operating in like a short window of time is service workers. Service workers have been around in modern web browsers for a few years now, and the intent behind service workers was to allow web applications to continue functioning even to some degree while the computer or the browser is no longer connected to the network. This is implemented by having somewhat like a background JavaScript execution environment. And it's really quite interesting in that they often have the capability to continue functioning even after a tab is in fact closed. They have some constraints in how they operate. In general, service workers must operate over TLS, except if you're developing on localhost. They don't often operate with mixed content. And also they also function in a somewhat sandboxed environment with a limited subset of JavaScript. There has been some interesting research though performed by Claudio and Emmanuel. They did some research for KiwiCon a few years ago and then also presented at DEF CON and Black Hat Arsenal, where they had used some tricks to actually coerce service workers to continue functioning in some circumstances up to 30 minutes. And if you think about it, 30 minutes is definitely a long time to be able to execute arbitrary JavaScript.
So I have a very simple service worker example here that's actually available on GitHub if you want to check it out. And if we look at the source code, all we're doing is basically loading a very simple service worker that just pulls localhost every second. And we can see I have a web server running in the background here. And when I visit the website, we'll see that polling kick off and see that there's a request made every second. But then when I close the tab, it doesn't stop. The polling will continue. And so you can imagine using this to launch CSRF attacks against either loopback or SSL websites from internal networks, and being able to persist these types of attacks even after the tab gets closed. With all of this context, let's go over a few real-world examples that I was able to identify using the techniques that we've gone over so far to find vulnerabilities in companies' internal infrastructure and report them through bug bounty programs. One example is using the reconnaissance techniques we talked about. I found a company was running a piece of software called Review Board internally. Review Board is a piece of open source software that's designed for code review. So I was able to pull it down and run it locally, and I had access to the source code, which makes finding vulnerabilities a little bit easier. Because this is meant to run internally, it doesn't have the same amount of scrutiny as edge-facing apps would. And because cross-site scripting and cross-site request forgery are such common vulnerabilities, it wasn't difficult to find vulnerabilities against this application. When put together, I was able to construct a link that, if clicked, would use cross-site request forgery to install a stored cross-site scripting on the application. That stored cross-site scripting could then be used to steal all of the source code at the company. So end-to-end, it's a link that, if clicked, steals all the company's source code, even though I didn't have access to Review Board. When I disclosed this vulnerability, the company decided that because they didn't write the code for Review Board, they weren't going to pay for it. I notified the maintainers of Review Board about the vulnerabilities, and they got it patched, and they credited me in the release notes. Here's another example. There's another open source tool called GOCD. This is a DevOps tool that configures environments internally. I used the same formula as before. I pulled it down, I ran it locally, and I took a look. By default, the application has no authentication, and that's an easier thing to exploit from an attacker's standpoint because it means anyone on the network can click it, and the victim doesn't have to be authenticated to the app to be able to trigger CSRF attacks. I found for the most part the application actually used CSRF tokens to prevent against CSRF, but there was one endpoint for creating environments that did not have CSRF protection. In this case, I actually knew the person running the bug bounty, and I reached out to them ahead of time and asked if this was worth submitting. They mentioned something similar to the first example, that because they didn't write this code, and because it's not in the scope of the bug bounty, it would not be worth submitting. And so I didn't. Here's one more example, and it follows the same formula. I found that a company was running a piece of software called GlobalSite internally. GlobalSite is an open source piece of software that I was able to pull off SourceForge, run locally, and look at the source code for. I was able to find a lot of vulnerabilities in this application, and among them included a reflected cross-site scripting and a remote code execution vulnerability that was due to being able to upload a web shell to a file upload endpoint. When combined, I now have a link that if someone clicks, the reflected cross-site scripting can be used to upload the web shell and detonate the payload for the web shell. And now we've gained shell access to a web server that we have no direct access to otherwise. When submitting this vulnerability, this company treated it differently than the first two companies did, and they recognized the security impact to their organization and decided to pay out for the vulnerabilities. I also worked with the upstream vendor in this case to get it patched. Hopefully this demonstrates how easy this formula is to be able to construct URLs that can cause some pretty nasty damage inside of companies' networks. Let's back up now and take the 10,000-foot view of all the different things we've talked about so far. Our main goal here is to see what's possible just through clicking a link and keeping a victim on a page for 60 seconds. So let's walk through a user story and see what that could look like, covering all the different things that we've talked about. The first thing we're able to do is grab the user's internal IP address using the WebRTC API. We'll assume that this phishing email was clicked via a mobile phone, making this attack possible. Using this IP address, we're able to immediately begin a timing-based attack to search other IP addresses that are within the same CIDR range for potential services that might be running on those hosts. In parallel with that, we can kick a service worker off that's able to run for many minutes in the background even after the victim has closed the tab. That service worker is then allowed to send cross-origin requests to all the HTTPS websites that we've been able to identify through our enumeration and reconnaissance step. This could include any CSRF attacks that we may have against these hosts, and we can interrogate them to see which ones are still active, again through timing leaks. Additionally, any cross-site scripting attacks that we're able to construct ahead of time based on the recon that we've done against the company, we can launch those as well. We might have to be a little bit sneaky about them, but usually we can get away with it by either iframing the reflected cross-site scripting payload in an invisible iframe, or by launching a pop-up, or by sticking it in another tab. While that's all all going on, our DNS rebind clock is also started. And what we're able to do there is we're able to iframe malicious domains for all of the hosts that we were able to identify from the ping sweep, as well as CNAME rebinds for all of the hosts we were able to identify from our enumeration step. And as long as they don't have SSL, in 60 seconds we'll be able to grab all of the content from all of those different hosts and proxy it back to the attacker, also priming the attacker for subsequent requests against those hosts. In concert, what we end up with is several avenues both to steal data and install backdoors into internal infrastructure. We also have several different avenues for persistence, including persistence on the victim's web browser through the use of service workers, and persistence on the servers that we're attacking, potentially through web shells, CSRF that allows us to store cross-site scripting or remote code execution. And we can do all of this even if the victim opened up the tab in an incognito window, just through the virtues of the phone sitting on multiple networks.
In closing, we think it's worth reiterating some of the reasons why we think web browsers are a really interesting target that you should be looking at on your next engagement, either as part of a bug bounty or a penetration test. Firstly, browsers operate in multiple different contexts and origins, and you should be using these as part of your assessments. Don't forget, modern web browsers are very mobile and they shift from network to network, and it's not like those browser tabs are closing as the computer or the mobile phone is moving around. Recon work for internal systems is also really, really important, and we think it's very valuable to spend time looking at open source products as well. Finding web application security vulnerabilities on internal systems can reap a lot of reward. And don't forget, new browser features are coming out all the time. They often play a bit of tug and war between, features that can provide new functionality to users, but also toe the line of potentially privacy impacting style scenarios. So, keeping across what's happening in the browser space is obviously very useful as well. And please, do test your internal apps. Just because there's a firewall there doesn't mean that you're protected.
You fill my headspace with evil thoughts unkind. I can do without.